Okay, part one of the chapter 21 homework is due on the 11th. Part two is due on the 18th. The 11th is Wednesday. The 18th is next week. Chapter 22 homework not due until after spring break. So, because we have a test and then spring break, basically. The chapter 19 through 21 review will be on the 16th. And the exam for 19 through 21 will be on the 18th. So that's next week. Review and exam. Like previous exams, you get a sheet of notes for reference. Let's get through all this. We were in magnetism. So let's talk about magnetic force on moving charges. So when you have a charge that is moving through space, it has a force on it. To figure out the force, the magnitude of the force is charge times velocity times magnetic field times the sine of the angle between velocity and magnetic field. And the direction, if you take your fingers and you point them in the direction of the magnetic force is actually defined based on this formula. So 1 Tesla is 1 Newton per amp meter. So the magnetic force on a moving charge is actually defined the magnetic field. You put your fingers in the direction of the velocity on your right hand. You bend them in the direction of the magnetic field, and your thumb will point in the direction of the force. That's what so point your fingers in the direction of the velocity, bend them, point them in the direction of the magnetic field. Your thumb points in the direction of the force on a positive charge. Negative charges go the opposite direction. So this is charge times velocity cross magnetic field. The magnetic field, velocity, and force, you can write it as charge times velocity cross magnetic field. What is this? Oh, Dominica. So, force equals QV cross V. The magnitude of force equals Q VV from the angle between them. So particle 1 with a charge of 3.6 microcoulombs and a speed of 862 meters per second. Travels at right angles to a uniform magnetic field. The force it experiences is 3.17 times 10 to the minus 3 newtons. So what is the strength of the magnetic field? So force is charge times velocity cross magnetic field. So magnitude of force is charge velocity B sine theta. Well, I forgot to put a vector arrow on top of the force. So magnetic field is force over charge times velocity times sine theta. So 3.17 times 10 to the minus 3 newtons times divided by 3.60 times 10 to the minus 6 coulombs times 860 meters per second times the sine of 90 degrees gives you a magnetic field of 1.02 Tesla, which is a pretty big magnetic field. Now particle 2 here has a charge of 73 microcoulombs and a speed of 1.61 times 10 to the third meters per second. And it's at a 55 degree angle to the field from the previous problem. So V is 1.02 Tesla. What force does the field exert on particle 2? So here, force is charge times QV cross B. So it's charge times velocity times magnetic field times sine of the angle. So 73 times 10 to the minus 6 coulombs times 1.61 times 10 to the third meters per second times 1.02 Tesla times the sine of 55 degrees. Okay, carry it here, but virtually 30. Oops, that was the wrong person. Which will give a force of 0.098 newtons. And questions? So the general rule to figure out which direction it's having, you can use the right-hand rule. So again, you point your fingers in the direction of the velocity, you bend them in the direction of the magnetic field, and your thumb points in the direction of the force on a positive charge. And that is force is charge, velocity, cross magnetic field. So here, given that the field below is out of the screen, and are the charges of each particle positive, negative, or zero? For particles 1, 2, and 3. Well, particle 1 is bending up, is taking this path. Particle 2 is going straight like this. Particle 3 is bending this way. So from out of the board, this is an arrow pointing out of the board. It looks like a circle with a dot in it. Into the board, it'll be a circle with an X in it. Because you're either looking at the point of the arrow, like this, or you're looking at the tail of the arrow with an X. So, looking at these, do you think the charge of 1 is positive, negative, or 0? Remember, right-hand rule, point your fingers in the direction of the velocity, bend them in the direction of the magnetic field, and your thumb will point in the direction of the force on a positive charge. So, if I take my right hand, I would start by pointing my fingers in the direction of the velocity. Demonstrating. Then I'm going to bend them in the my fingers in the direction of the magnetic field, and my thumb will point in the direction of the force on a positive charge. Number 1. Number 1 is negative. Number 2 is. Number 3 is, yeah. I found a nice 3D model that I'll print for you guys, but I need to set some stuff up. So I'll have it available on Wednesday. So if you have a particle with a charge of 5.75 microcoulombs and a speed of 351 meters per second, and it's acted on by both an electric field and a magnetic field, the particle will move along the plus x-axis. The magnetic field is 2. Okay, so you have this particle. It has a charge of 5.75 microcoulombs. It's moving at 351 meters per second, and it is acted on by both an electric field and a magnetic field. The particle moves along the plus x-axis. The magnetic field is 2.26 Tesla in the plus y direction. And the electric field is 1.16 newtons per coulomb in the plus z direction. So what is the net force on the particle? So this has forces from both the magnetic field and the electric field. And force from the electric field is just electric field times charge. Yeah. So we need to find the electric field and the magnetic field and figure out which directions they're in. So the electric force is going to be in the plus z direction because it's a positive charge in an electric field. The magnetic field, the magnetic force, well, we can point our fingers in the direction of the velocity, bend them in the direction of the magnetic field. The force is also in the plus z direction. X hat cross y hat is z hat. So force in the magnetic field is QV cross B. Force in the electric field is QE. So to work out the direction, it's in the positive z direction. It's QVB sine theta times z hat. And the electric field is QE z hat. So 5.75 times 10 to the minus 6 coulombs times 351 meters per second times 2.26 Tesla is 4.56 times 10 to the minus 3 newtons in the z hat direction. 5.75 times 10 to the minus 6 coulombs times 1.16 times 10 to the 3 newtons per coulomb. In the z hat direction is 6.67 times 10 to the minus 3 newtons z hat. The total is just going to be the sum of those. So 6.67 times 10 to the minus 3 newtons plus 4.56 times 10 to the minus 3 newtons, which is 1.12 times 10 to the minus 2 newtons. 0.0 0.012 112 newtons. So you just need to work them out individually. It's just helpful to know, just for remembrance, x hat cross y hat is z hat, y hat cross x hat is minus. Order matters. So here we have a positively charged particle that moves with a velocity v in the magnetic field B shown. Does the force point into or out of the screen? So here, do you think the force on this particle, so here, this is the velocity, this is the magnetic field, is the force into or out of the screen? What do you think? It's actually in. So you point your fingers in the direction of the velocity, bend them in the direction of the magnetic field, and your thumb points in the direction of the force on a positive charge. So here, velocity, magnetic field into the screen. If the magnetic field was going up, was on the other side of the velocity, was over here, then it would be out. I'll just keep going. So magnitude of the magnetic force, charge times velocity times magnetic field times sine theta. That is used to define the magnetic field. Why do I feel like this is just repeating? Let me just check this. Okay, that was repeating. I'm not sure why. I need to clean these slides up apparently. So, because that was repeating, and I need to hide things apparently. Here we have a positively charged particle in an electric field experiences a force in the direction of the field, as you can see here. In a magnetic field, the force is perpendicular to the field. And this leads to very different motions. So if you fling a, if you have a constant magnetic field and you fire a charged particle into it, and you have a constant electric field and you fire a charged particle in it, you get very different motion. In a constant electric field, the particle gets accelerated towards the direction of the electric field. It moves that way. But because the force is perpendicular to a magnetic field, you fire a particle in perpendicular to a magnetic field, it goes around in a circle. So electric fields drive particles in the direction of the field. Magnetic fields cause charged particles to circle around them. Because the magnetic force is always perpendicular to the direction of motion, the path of the particle is circular. And also, while an electric field can do work on a particle, a magnetic field cannot. The particle's speed will remain constant. You have a constant magnetic field. So if you have a particle of mass m and charge q moving at speed v in a magnetic field b, the radius of the circle it travels in, r, is mass times velocity over charge times magnetic field. So you can get this with some force equals mass times acceleration. So charge times velocity times magnetic field. Acceleration is v squared over r. So charge times velocity times magnetic field is then v squared over r. One of the velocities cancel. And if you solve for r, you get r equals mv over qb. So the radius of the circle that a charged particle has, if it's perpendicular to a magnetic field, is mv over absolute value q times the magnetic field. The sign just determines which way around it goes in a circle. Clockwise or counterclockwise, kind of thing. And one of the ways you can measure the mass of particles is in a mass spectrometer. You can have ions that have a charge in a magnetic field, and you can basically use the radius that they form. They'll move in circles of different radii, and you can separate things out by their mass. So in this example, we're separating uranium-235 from uranium-238. You can separate out uranium-235 from uranium-238 because their radii will be different because they're proportional to the mass. And they'll be slightly different. It was actually used to separate uranium. One of the ways they separated uranium in big centrifuges I mean, in big synchrotrons for the original atomic bomb. You can separate different elements and isotopes of the same element. You can basically measure the mass of things. You can also use it to get information about, molecules in a mass spectrometer. So this is not the only way you can separate things out by mass to charge ratio. So this basically, you have a guaranteed way, fixed velocity and magnetic field, and you separate by mass to charge ratio. And if a particle's velocity makes an angle with the magnetic field, the component of the velocity along the magnetic field doesn't change. The particle with an initial velocity and angle to the field will move in a helical path. It'll spiral along the magnetic field line. And this spiraling along the magnetic field lines is actually what protects Earth from things like the solar wind. Earth's magnetic field redirects charged particles coming from the sun. They bounce back and forth along the field lines. And if they hit the atmosphere, you get the northern lights, auroras. So the radius, if it's at an angle, it's the perpendicular velocity, which is, v sine theta. So it's the radius is mv sine theta over charge times magnetic field. So this is a device called the velocity selector. It basically separates charged particles out by their velocity. Charged particles move through a region of space with both an electric and a magnetic field. And if the speed of the particle has a particular value, the net force acting on it is 0. So assume that a positively charged particle moves in the plus x direction, as shown here, and the electric field is in the plus y direction. So the electric force will be in the plus y direction. Should the magnetic field be in the plus z direction, the minus y direction, or the minus z direction in order to get a 0 net force? That is correct. Because you'd like to get a force in the minus y direction. Your velocity is in the x direction. And if your magnetic field is in the plus z, your force is in the minus y. So if you have an electron that's moving perpendicular to a magnetic field of 4.31 times 10 to the minus 3 Tesla, and it follows a circular path of radius 3.7 millimeters, what is the electron speed? The charge of an electron is 1.6 times 10 to the minus 19 coulombs. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. And the appropriate radius is mass and velocity over charge of magnetic fields. So I will give you a few minutes to work on this. So radius is mass times velocity over charge times magnetic field. The radius times charge times magnetic field is mass times velocity. The velocity is radius times charge times magnetic field over mass. So that's 3.70 times 10 to the minus 3 meters, 3.7 millimeters, 1.6 times 10 to the minus 19 coulombs. That's the charge of an electron. 4.31 times 10 to the minus 3 Tesla. That's our magnetic field, all divided by the mass, 9.11 times 10 to the minus 31 kilograms. And this electron is moving at 2.8 times 10 to the 6 meters per second, which is pretty dang fast. It's almost 1% of the speed of light. So here, we're separating two isotopes of uranium, uranium-235 with a mass of 3.9 times 10 to the minus 25 kilograms, and uranium-238 with a mass of 3.95 times 10 to the minus 25 kilograms, so 3.90 versus 3.95 times 10 to the minus 25 kilograms, are sent into a mass spectrometer with a speed of 1 times 10 to the 5 meters per second, as indicated in the sketch. Given that each isotope is singly ionized, that means the charge is 1.6 times 10 to the minus 19 coulombs. It's 1e. And that the strength of the magnetic field is 0.75 Tesla. What is the separation distance d between the two isotopes after they complete half a circular orbit? So here is an image showing that. So you can see this. Uranium-238 is going to travel twice the radius for uranium-238. Uranium-235 will travel twice the radius for 235. So 2R-238 minus 2R-235 will give us that distance d. The radius is mass times velocity over charge times magnetic field. So mass 235 times velocity over charge times magnetic field is radius 235. Radius 238 is mass 238 times velocity over charge times magnetic field. So distance is 2r238 minus 2r235. So 2 times s 238 times velocity over charge times magnetic field minus 2 times mass 235 times velocity over charge times magnetic field, which is 2 times the difference in mass between 238 and 235 times velocity over charge times magnetic field. So 2 times 3.95 times 10 to the minus 25 minus 3.90 times 10 to the minus 25 times 1.05 times 10 to the 5 meters per second, all over 1.6 times 10 to the minus 19 coulombs times 0.75 Tesla gives a distance of 0.00875 meters, or 8.75 millimeters. Any questions about this? So here, instead of asking about, this is asking, figure out the time t required for a particle of mass m and charge q to complete a circular orbit in a magnetic field of strength v. You'll notice the velocity is not given here, because it turns out the period t, you can calculate velocity will end up canceling out. So that time t is 2 pi times the radius divided by the velocity. So just check. Okay, I'll just. The radius is mass times velocity over charge times magnetic field. The period t is 2 pi times radius over velocity. So if we plug in our radius formula into that, we get 2 pi over velocity times mass times velocity over charge times magnetic field. Velocity cancels, and we get 2 pi times mass over charge times magnetic field is the period. So the period is independent of the velocity you send it in, which is actually quite convenient because it allows you to, if you have a fixed magnetic field, you can basically measure charge to mass ratio by measuring how fast it goes around in circles, which is actually pretty easy to measure because it'll be an accelerating charge, and that gives off electromagnetic radiation. So a particle orbits in a magnetic field with a radius of 1 meter. If the mass of the particle is doubled while everything else remains the same, what will the new radius of the orbit be? Will it be 4 meters, 2 meters, 1 meter, or half a meter? That is correct. Because we double the mass, that doubles the radius. And I think that is where I'm going to stop for today. I'll see you guys on Wednesday. we'll have another live event.